This is a video for the Growth Models writing assignment. It's an example of one of the two problems you'll need to do for this assignment. So you should go to the our web page, and you can click on, you can either use the block or you can just select the calendar day when it's due, go down and open the assignment in this way. You should go ahead and read through the instructions. I'm going to give you the instructions as I go along. There's a lot of options for you to pick from, and some of these will be exponential, better for exponential, and some will be better for linear modeling. And you can just pick any, pick a few that you like, look at them and see which one would be better for exponential and which would be better for linear, and then our example will show how you determine which one it is better for. So I'm going to use, this is the example one, is the Florida population growth. It actually can be used for either one, so I'll show you why. So as we look at the Florida population, you should note that it goes from way back in 1840 all the way up to 2020, and I'm not going to use all those values, but if I wanted to use this for linear, I would probably just pick values from like maybe 1980 up to 2020, because that looks like a pretty straight line. But I'm going to use it for exponential, so I'm going to go from back here in 1940, and then so you can see it curves. I mean, it might be better to go back all the way to 1920, but I already done these values. I picked from 1940, and notice that some of these graphs will have like the data values on them. Notice as I move my cursor, it tells me the 1940 population was 1.9 million, and then 1950s 2.8 million, 1960s 5 million, and so on all the way up. And so I recorded all those values and I put them in a table, and I'm going to show you what you'll need to do the same thing. You'll need to record values, ordered pairs, record them in a table similar to what I do, and you'll need to do this twice. You'll need to do it for one for an exponential model and one for a linear model. In the assignment, it wants you to put the linear model first and then the exponential model second. I'm just going to make a document, and so I can just upload it on whichever one is appropriate. So let's go ahead and take a look at what I did. I gathered all that data, I wrote it down, and then I had it and I put it into a table. So here's how I made a table. I made a table in Word, and so I'll just show you how you can do that. I put insert a table, and I was going from 1940 to 2020, really, 2020, and I went up extra lines. So that's like 9 lines, and so I made it 12. Now I want the year, so that's one column will be a year. The next column was going to be the population. The next column would show the differences, and the next column would show the ratios, because I need to compare the differences in the ratios. So I've got to have 4 columns, and so I'm just going to insert it. I'm going to 4 columns, and I think there was 9, so I'm going to make 10, 12. I'm going to make 12 rows. So that's how I did that. And then I labeled the rows. I went year, and then population, and you'll see in the next slide I've done all this, and I wrote all the data down, and then so I'll show you what that looks like now. So with all that information filled in, it looks like this. So in 1940 the population was 1.9 million, and then so on. And what I did was I wanted to start in 1940, so I'm calling 1940 0. That's my 0 year. And then 1950 is 10 years later, and so on. And so I wrote all those values down, and then I'm going to make a prediction for 2030. That's 90 years after 1940, so that's my N value basically, is going to be 90. And so we'll see, here's all the values, and then we're going to be guessing, we'll use an equation to estimate the 2030 population. And so here's what you need to do. In both cases, whether you end up using the common ratio or the exponential or linear. So for the linear, the common difference, if these linear differences, these you get from subtracting. Now, I made this a little harder than I needed to, in some way harder, because these go every 10 years. So when I go 2.8 minus 1.9, that is not an annual difference, that's a 10-year difference. So I had to divide by 10 each time. So 2.8 minus 1.9 is 0.9 million, but that was over a 10-year span, so I had to divide by 10. Now, if you just go by the year, if it was like 2010, 2011, 2012, 2013, you would not be dividing by 10. It would be a lot easier than this. So you just have the 2.8 minus 1.9 or 5 minus 2.8. So anyway, if you get one that's trickier, you'll have to do something like that. So I'm doing a harder one, and you don't have to do that if you don't pick values that far apart like I did. So anyway, this 0.09 is 0.09 million, which is really 90,000. 90,000 more people per year. See, in a 10-year span, so I divided by 10. This is 220,000 people per year, or 0.22 million, and 180 million per year, or 180,000. So notice these are not very consistent. 0.09, 0.22, huge change there. 0.18, 0.29, look how they jump around. Then 0.32, it's getting a little smoother because remember that picture, it showed it was closer to linear just at the top end. So these are a little closer to linear. And then what I did is to find the average of all these, I just took the 21.7 minus 1.9, and that since that's an 80-year span, you just divide by 80. So if yours was like a 10-year span, you would divide by 10, or whatever, 8 years. I'd expect you to take at least 5 or 6 data values. You shouldn't just do it on like 2 or 3. That's not sufficient to get a model. You have to have several data values. So anyway, that's the average. It's about 0.25 million per year, or 250,000 if you will. Now to do the common ratio, you divide subsequent, right? 2.8 divided by 1.9. Now of course this was a 10-year span, so I had to take the 1/10 power of those, or the 10th root. So I had to raise this to the 1/10 power. 2.8 divided by 1.9, all of that to the 1/10 is 1.0. It's really 1.0, I can't remember, 39 or something, but I rounded off to the nearest hundredth. And then similarly, instead of 1/10, I use 0.1. It's the same thing, right, as a decimal. So I did all these divisions. I divided all the way, took the 1/10 power, and here are the ratios. Now those are a lot more consistent, aren't they? This is 1.04, 1.06, 1.03, 4. See, these are much more consistent. This is not perfect, but it's I think it looks better than this overall. Now at the end, these look pretty good, and these look okay, but these you can see are getting smaller, and I'll comment on that at the end of the lesson. But anyway, so now for the overall, the 80-year span, we don't add these up and divide by 10. You take the 21.7 divided by the 1.9 and take the 1/80th power of that. Okay, and that gives me 1.03. So that means there was a 3% growth rate average over the last 80 years. So I'm going to pick, it looks to me like the ratios are more consistent than the differences, which would make an exponential model a better fit for the data that I chose from 1940 to 2020. Now, it doesn't make the exponential model the best model, but it is better than the linear one anyway. From that span, from 1940 to 2020, the exponential is a better model. And again, it's not ideal. Now, if I'd chosen from like 1980 to 2020, it could have been that the linear model would be just about as consistent, but I chose to go from 1940. So anyway, this means that the form of the equation for the model should be this. This is the exponential form. P sub n is equal to P sub 0 times B to the n. And remember, B is our common ratio, or our consistent or average one. So P sub 0 is the starting value, so that's 1.9, which represents the population in 1940 in millions. And B is 1.03, you did that, and that indicates that the growth rate's 3%, or because R is, remember, B minus 1, or 1 plus R is B, so we get this. So here's my formula. 1.9 is my P sub 0, 1.03 is B, and it says I want to predict the population of Florida in 2030. So using my model, n is equal to 90. So remember that? If, remember 2020 was 80, so 2030 is 90 more than 1940. You can just, 2030 minus 1940 is 90. And so I plug that in, make my prediction, that's 27.2. And remember, the estimate, I need to write out what it means. You should write this out. The model is 27.2 million people in 2030. I wouldn't want to just write 27.2 because that doesn't really make a statement. We want to write a complete sentence here. Okay, and that would be sufficient there. I'm just going to add an extra comment here. You don't need to add this. The model clearly had a problem since the ratios were getting smaller, right? Those were going smaller, 4, 3, 2, 1, 1.0, down to that. And so using 1.3 is most likely to give a too large of an estimate. 27.2 million is probably bigger than it really will be. And there are better models than this one. But I just wanted to use this as an example. So that's all I have for this, and I hope that helps. You can watch that multiple times if you need to get a better idea of what to do.